Okay, this is the second lecture on chemical and phase equilibrium. In the first lecture, we derived a criteria for chemical equilibrium and came across the notion of the equilibrium constant. In this lecture, we will take the idea of equilibrium constant further and see what its implications are. Then we will examine what the equilibrium constant depends on and how it influences systems. That will bring us to the end of chemical equilibrium, after which we will move on to phase equilibrium. So, to recap, we derived equilibrium constant as K p, which is a product of the partial pressure of the reactant species, the product species to the standard pressure raised to the power its stoichiometric coefficient. So, C, D, E, F, all these would be product species, and in the denominator would be A, B, C, D, which are the reactant species. And this is for a mixture where all these species are present together. So, we say that if I have a mixture like this, in which I have some A, some B, some C and some D, then this tells you what is the equilibrium constant for this particular system, which is at a temperature T and P. Now, we rewrite this constant, the equilibrium constant, defining that P I is Y I into P, or in the partial pressure Y I is the molar fraction N I by N mix, which is the total number of moles in the mixture. So, either we can write mix or we can write total. So, K p then becomes the molar, the number of moles of each species to the power of its stoichiometric coefficient. The reactants are, the products are in the numerator, reactants are in the denominator, multiplied by P upon N mix. N mix, as we are saying, is total. This whole thing raised to the power delta nu. Delta nu is nu C plus nu D, like that for the products, minus nu A minus nu B for the reactants. So, in a summation form, delta nu is summation of the number of the stoichiometric coefficients of each of the product species minus sum of the stoichiometric coefficients of the reactant species. So, it is this minus, one can call this as this. So, this is rewritten again as y c to the power nu c into y d to the power nu d, similarly for the products, multiplied by P over P 0 to the power delta nu. Remember, P is the system pressure, total pressure, and P 0 is the standard state pressure. So, we have two more expressions coming up from our earlier definition of the reaction, the equilibrium constant. One could be in terms of the moles and the other in terms of the mole fractions. They are all equivalent as long as the substance is in gaseous state. Now, we put this expression back in the relation that we had. Now, delta G 0 becomes minus R u T ln K p, where that it was this big expression over there in this equation there. This is what we had. All of this was R u T ln all of this, which was d G mix T. So, now we know that this whole thing it become K p, and our expression becomes much more elegant, that delta G T at 0, or you can even some cases we write this as delta G 0 at temperature T is minus R u T ln K p. And so, we now get a new expression that K p can be expressed, the equilibrium constant, as exponential of minus delta G 0 T upon R u T, R u being the universal gas constant. This is an important expression in all of chemical reactions. We can express delta G T 0 as in terms of enthalpy and entropy, and then K p is exponential minus delta H 0 upon R u T minus exponential delta S 0 upon T. So, this is yet another expression we get. which is the same as from there. So, what it tells us is that if K p is greater than 1, that means reactants are headed towards becoming products. This implies that delta H 0 is less than 0, which means that the reaction is exothermic. So, this is the type of implications that we can see from this expression. Now, we will look at K p in more depth and the case of ideal gas mixtures. So, what we have is that K p could be expressed as partial pressures, in terms of partial pressures. So, all of that is done, or in terms of the molar fractions. I will not rewrite this equation, we already have this before us, and that K p can also be written in terms of the standard state Gibbs function as K p is equal to e to the power minus delta G 0 t upon R u t. This is the same expression that we have got earlier. So, there are two ways in which we are able to express K p, once as the partial pressures or in molar fractions, or as standard state Gibbs function. What it tells us that if we know delta G 0 t from thermodynamic data, we can calculate K p, or here if we know partial pressures of the molar fractions, then we can get K p. So, there are two different ways that take us to the value of K p. And the third one, in terms of moles, that K p was n c to the power nu c n d to the power nu d upon n a to the power nu a and d to the power nu d multiplied by p upon n total to the power delta nu. Now, what we will do is we will look at these expressions and say, well, what can we interpret from them? So, there are several characteristics of this K p that will come out. That first, K p, which is a function, which is unique value at every temperature, is not only a function of T, is only a function of temperature and is not a function of pressure. So, an expression like this H 2 plus O 2, H 2 plus half O 2, equilibrium at this is same at 1 atmosphere, 5 atmosphere or 20 atmospheres. Then in this expression, if we added inert gas like nitrogen, then also the K p value does not change, and it does not matter whether this mixture is at 1, 5 or any other pressure. And even if this expression, in this particular case where H 2 and O 2 are in their elemental states, H 2 plus 2 O 2 plus 2 N 2, leaving an excess of oxygen on the right side in the products, this also at any pressure, then all these reactions at any pressure, they have the same K p t. So, this is one characteristic about K p. The second thing is that K p, as we have defined, is the equilibrium constant that comes from the forward reaction. For the reverse reaction, everything is just, instead of left to right, is right to left. The equilibrium constant for the reverse reaction is 1 upon K p. So, the reverse reaction equilibrium constant is K p to the power minus 1. Then the third thing about Kp is that as Kp is large or is big or greater or increasing, the forward reaction will go to a larger extent. So, larger the value of Kp, this implies more of the forward reaction will take place. And which tells us basically that the reaction will proceed more towards completion. The reaction will become more complete. That is, more of the reactants become more of the products. If we want 100% of the reactants to become 100% of the products, which basically would require that Kp should tend to infinity, which means that in some cases we say that it reaches pretty much there, but not exactly there. So, it never exactly goes there. For example, if you were always looking at methane burning, and we always said that this always produces CO2 plus H2O, and that the reverse did not happen. In practical situations, earlier we would say that yes, this is what happens. When we are worried about emissions, well, we have to worry about the fact that some of this could get decomposed and form CO and O2, and so the exhaust or the emissions would include carbon monoxide. So, Kp, although it has gone to a very large extent in burning out all the fuel, there is always a very small amount which is still not completely burned. So, what we are saying is that if Kp is of the order of or greater than 1000, which says that ln Kp is more than 7, then we can say that practically almost all the reactants are converted into products. On the other hand, if Kp is very small, the equilibrium constant is very small, it means that the reaction cannot proceed. And it is the opposite of this, that if ln Kp is of less than of the order of -7, then we say that practically the reverse reaction will not happen. The reaction itself will not happen. So, this would be an example that we just take a piece of say carbon and keep it in atmosphere, and we say, look, I have carbon, I have oxygen in the atmosphere, is this reaction taking place? Well, the answer is yes, because of Kp being very, very small, this reaction is produced an equilibrium which is very small and it is not going to be proceeding much faster than this. Then the fourth thing about the equilibrium constant, that the pressure of the mixture, that is P total or P mix, this affects the equilibrium composition. And that is because in those expressions that we have derived, Kp is a function of P to the power delta nu. Delta nu, you recall, is the sum of the stoichiometric coefficients of the products minus sum of the stoichiometric coefficients of the reactants. If delta nu is 0 or very close to 0 or very small, then pressure does not affect Kp. So, there is no effect of Kp. But if delta nu is greater than 0, that means more moles are being added. That means number of reactant moles is going up and number of product will go down. So, as pressure increases, more products will be formed and more reactants will be there and less products will be there. Opposite is the case when delta nu is less than 0. Now, we look at the effect of inert gases, And this is of interest because air as the oxidant is always got very large amounts of nitrogen, which for practical purposes we treat this as an inert gas. So, if you are burning CH4 plus O2, how will it be different from CH4 O2 plus 3.76 N2? This is the question that is before us, and what we say is that inert gases affect the value of the equilibrium constant. Why so? Because we have seen earlier in the expression that we have Kp is proportional to 1 upon n, the total number of moles in the mixture. So, this is nothing but n mix, which is summation of Ni for all the species that are there in the mixture. Now, when you have only this, you have 1 plus 1 2 moles. When you have this, you have 1 plus 1 2 plus 3.76 5.76 moles. Earlier you had 2, now you had 5.76. So, this is what is changing. And what will happen in this case is it is raised to the power of the same delta nu, the difference in reactant and product stoichiometric coefficients. If delta nu is equal to 0, the presence of inert gas has no effect. If delta nu is greater than 0, then as the number of moles of inert gases goes up, this comes down and the products moles goes up, and the opposite will happen if delta nu is less than 0. So, there is some effect of the inert gas depending on the delta nu factor. Then what if you have the same reaction but written in different moles, such as H2 plus half O2 going to H2O, but now we multiply everything by 2. So, this is reaction 1, and we say now the reaction 2 is H2 plus O2 goes to 2H2O. Is the equilibrium constant in both cases? What will happen is Kp for this reaction will be partial pressure of H2O upon pH2 and oxygen partial pressure to the half, but in the second case this will be pH2O square upon pH2 square upon PO2, which is Kp for the first reaction squared. So, the multiplication factor for the number of moles in the reaction. So, this is whatever x into something that shows up as an exponent over here. If it is 3 times here, this will become cube. It is half, this will become half. So, what we have seen is that all nus are increased or decreased proportionally, then this affects the equilibrium constant P. And then we say, well, what else is it applicable to? Because in many chemical reactions, there are a lot of radicals being formed, and in some cases even free electrons. So, if an reaction like H becoming H plus E minus, or there are radicals like say OH minus radical in a chemical reaction, then free electrons and radicals, if they are present in the reaction, we can treat them just like an ideal gas. This is particularly the case. We cannot ignore this particular type of reaction at high temperatures. For example, when a spacecraft is entering the Earth's atmosphere, or for that matter leaving the Earth's atmosphere, this is an important consideration. And in combustion reactions, which are all multi-step reactions, there will be radicals, and so we will have to account for it in the same way. And last point to note about Kp is that this is only about equilibrium, and this is the equilibrium state, and it tells us nothing about the reaction rate. So, if you want to ask the question what is the rate at which this reaction will take place, Kp is not the one to tell us what is going to happen. So, we do not know anything about this from Kp. Then there are effects of catalysts that we can factor in, and finally, the fact that Kp depends only on temperature. So, question is how does it vary with temperature. So, if you have two states at T1 and T2 and Kp defined in the same way, then we can rewrite this in terms of G H and Ts, where this and this are for reactants and the products, and differentiating we get this expression, and at constant P, which we get Tds is equal to Dh, this expression becomes Hr bar times T Ru upon T square. Hr is the molar enthalpy of reaction. So, we end up getting a nice elegant expression from here, and what it tells us is that for small changes of T2 to T1, ln Kp2 over ln Kp1, where ln Kp2 is reaction the equilibrium constant at T2, this is equilibrium constant at T1, this is Hr bar over Ru1 minus T1 upon T2. So, far we can get a very quick idea about the heat of reaction from this, and it tells you that as T2 increases, if Kp2 decreases, then we have exothermic reactions, and it will be less complete. So, this is an interesting equation which connects equilibrium constant to the molar enthalpy of reaction. So, one side you have Kp and the other side you have Hr bar. This is called the Van't Hoff equation. So, that brings us to the end of chemical equilibrium, and we have seen that we have the equilibrium constant and what all it depends on and how it is influenced by different parameters. We now come to the topic of phase equilibrium, and we are now looking at situations where you have three phases which can possibly exist in equilibrium with one another: saturated liquid, saturated vapor, or even call it dry saturated vapor, and saturated solid. So, we have several possible combinations. These two could exist in equilibrium, liquid and vapor, which is what we called earlier as a wet state. This could also be existing there together, liquid and solid, and the third one is vapor plus solid. So, what is the third thing that is there is when all of them are there together, and that is at the triple point. So, this was liquid plus vapor, liquid plus solid, vapor plus solid, and then a triple point. So, now let us see what is the condition that tells us that equilibrium will exist when two phases are present simultaneously, first in a single component system, then very briefly we will look at multi component systems. So, we are looking at, we will take the case of saturated liquid with subscript F, saturated vapor subscript G, consistent with what we have learned so far, and G for a mixture. So, this is a mixture, a system in which there is this much of the liquid F, this much is the vapor G. Then the Gibbs function for this mixture is MFGF with the specific Gibbs function plus MGGG. So, we are using G as subscript to denote the vapor phase. Now, what will happen if there is a small change from saturated liquid to saturated vapor or vice versa? So, this will result in a small change in the Gibbs function dg at T p is this we can then write this as G f into d m f, a small mass of liquid that disappeared, plus G g d m g, and this will be with a minus sign because this would have decreased. And since the liquid became vapor, the two masses in quantity are the same. So, they are equal and of opposite sign. So, we can simplify this to write as G f minus G g into d m f, and which tells you that at equilibrium this parameter has got to be 0, which means that G f is equal to G g. So, this is something we can say that is come out quite explicitly, that for a two phase mixture in equilibrium, the each phase has to have the same value of the Gibbs function, that is G f is equal to G g, or in molar terms G f bar is equal to G g bar. And this is true for any of the other combinations of mixtures also. So, what it basically tells us here is that if we look at the property data that we had looked at right in the beginning at the pure properties of a pure substance, in the property table what was listed was P, T, H and S. In some cases U was also listed, but by and large G was not listed. U was not listed because U could be calculated as H minus P v, and G can be calculated as H minus T s. So, what this thing is telling us, that if we take a saturated state and get these data from the table for the vapor phase and get these data for the liquid phase and do the calculation and get G f, G g for vapor and G f for liquid, these two values will turn out to be equal. This we can verify for any substance. In three phases, this logic gets extended, and the only way you can have equilibrium is G f is equal to G g is equal to G s. Again, you can look up the property data and verify this for yourself. So, what will happen if these were not equal? So, we say if G f is not equal to G g and say G f is greater than G g, or we have the second case where G f is less than G g, then according to say we take this case, the second law says that d g at T and P, this is equal to G f minus G g d m f, this is less than 0, this has to be less than 0, this part. So, which tells you that d m f has to be less than 0, which implies that some of the liquid will become a vapor, and it will do so until G f is equal to G g. So, in some sense what we are saying is that we are able to get the direction in which phase change will take place, this way or that way, by looking at the value of G. So, we get another important conclusion coming here, that G is the driving force for phase change. So, this is a simple thing that has come out, but it has got far reaching implications, and we look at engineering of complex systems. This is what we will end up using. So, that was simple for a single component phase, that G f is equal to G g, that the phase Gibbs function for each phase is the same, then we have equilibrium. Now, let us look at the more complicated case of two components. And what are the examples of that? There is water and there is air over there, and we are interested in finding out what happens in a small layer over here and a small layer over there. So, what we are asking is, in the air which is just above the surface of the water, how much water is there, and we have equilibrium. And we ask the opposite, that how much in the small layer just below the surface of the water, how much air has come over there. So, this has got many applications and implications. In nature, we have oceans and waters where this thing is happening. So, you have some air always getting dissolved in water, and by the type of equilibrium calculation that we will just look at, we can estimate how much air is dissolved in water. And when we say air is dissolved in water, it basically means that either you have an oxygen molecule or a nitrogen molecule. So, that means that water is slightly aerated, and we know from experience that this is enough for the seas and the lakes and the rivers to sustain marine life. This is very important. This is also a fact that the water we drink has air in it, but the same water were to be used in any process where steam is being used, like what you learnt in the Rankine cycle, then as you heat it, what will happen to this oxygen and nitrogen? If they begin to get out, then this oxygen will react with, say, many of the elements which form the material of the tubes and of the surfaces start reacting, and that is not nice. Another example could be that if instead of air we have carbon dioxide and we pressurize it. So, now what we have done is pushed carbon dioxide molecules into the water, we got what we call a carbonated drink. So, these are the type of applications that we can look at. Some other things is applications are that if you have an oil drop, sort of a fuel, which has been sent into an atmosphere, which like happens at the end of a compression stroke in a CI engine, then you have very high pressures and high temperatures over there. One thing we were looking at is that these molecules will go out there, mix with air and start burning, but now we got to worry about some things, that if the pressures are sufficiently high and the properties of the oil are certain, then some of this air will start going into the oil and alter the properties of the drop surface, and without that we will not be able to accurately predict how this particular fuel will burn. And this is especially then the other application in that if you are trying to have something like biodiesel, where you have HSD and some biofuel, some sort of an oil or a vegetable oil, which is a much heavier molecule, C16, C20, something like that, versus HSD, which is C10, then these two are not going to exactly mix with one another, and they will, how they will behave and what will be their equilibrium behavior like, this is something we would like to know. So, these are the type of applications that we are looking at for two component in two phases. So, we are saying that we will not consider a situation where there is no driving force between different phases of each component, i.e. GFI is equal to GGI. That means, for each species, GF, say for air, would be GG for air. So, this is what we would do when we are looking at ammonia water mixture in the vapor phase and ammonia water mixture in the liquid phase, or at air mixture of oxygen and nitrogen air, which is at very low temperatures of the order of 77 K to maybe 120 K, where some of this oxygen and nitrogen may start becoming a liquid. So, this is one assumption we start with, and what we say is that in this case, say water air thing. So, this is water, on this side above that there is air, this is at T air and this is at T water, which need not be the same. And now, what we are saying is what is the equilibrium condition over here, and for that we might have already used this in some cases, that the partial pressure of water in the air just above the water surface will be equal to the saturation pressure of water at the water temperature. or strictly at the interface temperature. If the two temperatures are not very much different, that doesn't make much difference, but if they are very widely different, then we have to worry about the interface temperature. What we are saying is that the liquid just at the surface or below the surface over here and the vapor here are in local thermodynamic equilibrium. But that does not mean that this is a static system. Like chemical equilibrium, phase equilibrium is also dynamic, which means that at any instant some molecule is leaving the liquid phase and coming into vapor phase. At the same time, a molecule from vapor phase is going back into the liquid phase. So, this going back and forth is happening, but if we take a snapshot of the entire macro level system, it is invariant. Then what happens on the water side? We know from experience that air is weakly soluble in water, and so YH2O on the liquid side will be practically 1. The mole fraction of air in water is going to be extremely small. So, one of the key ideas here is that Y in the gas side is proportional to Y in the liquid side. So, this is important thing from which lot of things will come out. First, Pi on the gas side is proportional to P times Yi on the liquid side, where Yi is the ratio of partial pressure to the total pressure. So, we can modify this slightly and get an expression that Yi on the liquid side is equal to Pi on the gas side divided by H, which is the constant, and this is called Henry's law. So, for a limited class of problems, we have Henry's law telling us what is the equilibrium condition at the interface. This is valid at very low pressures and for mixtures of liquid and gas. So, here is one important expression we got to predict what will be the composition of these layers. The same expression, when it can be recast, becomes Pi on the gas side is equal to H times Yi on the liquid side. So, the question is, how do we get the value of H? And for that, there is a lot of data has been tabulated for different combinations of liquids and gases at different temperatures. So, we can look up the problem, say in this case we are looking at air and water, we can look up air water data and from there get the value of H, use it here and start predicting these things. So, what this expression tells us is that the concentration of gas dissolved in the liquid is proportional to 1 upon H. Larger the value of H, less is the concentration of the gas dissolved. Then, as T increases, the data will show from the tables that H increases. So, if you look at this point here, that means if H increases, concentration of gas dissolved in the liquid goes down. So, the implication now is that concentration of dissolved gas in liquid goes down. So, this is something which is important when we look at practical engineering of power plant cycles or steam based using steam as a working substance, especially at higher pressures and temperatures. If you look at this relation, then for water with say oxygen or nitrogen in it or air, at temperatures of like 80 degrees C and definitely around 150 degrees Celsius, if you just warm up the water and keep it, lot of the oxygen and the nitrogen or the air that was dissolved in water has been expelled. In that, if you put some marine life, it will not be able to sustain. At 150 degrees Celsius, the driving out of oxygen from water is much more, the concentration of dissolved gas is far less. This process of say heating water and driving out the dissolved gases is called the opposite of what we saw by putting it in, deaeration. And this is very crucial in steam systems, especially large power plants. And that is the way one does it. Then we have seen that concentration of dissolved gases in the liquid is proportional to partial pressure of the gas. So, what is partial pressure of the gas, which is the surrounding total pressure. So, if P goes up, dissolved gas concentration goes up, and that is the idea of aerating water, that you increase the pressure and dissolve some gas into it. The gas could be carbon dioxide, which is what we have actually in aerated drinks. Then this entire idea is applicable only for weak solutions at their interface. In that, if you want to predict the concentration of oxygen deep into the sea, this is not going to give us the correct answer. This is good enough for a small layer near the surface of the water. So, what do? We have learnt a limited application of two-phase, two-component equilibrium. What if you have strong solutions? And this is what we encounter in things like the burning of biodiesels or solutions in vapor absorption systems. In all those cases, we cannot apply Henry's law. Then there are more advanced techniques that we have to use, one of which is Raoult's law. We will not go too much into the detail of these, where it says that Pi on the gas side is equal to Yi gas side multiplied by the total pressure, which is Yi on the liquid side multiplied by Pi at saturation partial pressure of ith component at T. And again here T is some sort of an interface temperature. So, we will leave this at that, and that brings us to the conclusion of phase and chemical equilibrium. So, we can now summarize what we have. We started off by looking at 3 different systems, and for all cases we said that delta G less than 0 is where the processes will take place, and the condition for equilibrium, whether a reacting system a two-phase single component system or a two-phase multi-component system. In all cases, we are looking at dG equal to 0 for a given temperature and pressure. This is the condition that will ensure there is equilibrium. So, that is what we learnt was a new property, the Gibbs function, and not just H minus Ts, but its implication on the processes that bring about equilibrium. Then we developed the idea of an equilibrium constant, and saw how it is affected. In doing that, we will also require values of Gi, which is the Gibbs function for any material at a particular temperature, and this data we can get as the G0 data from the same tables where we have looked at H0 data, and from there we can use this in these equations. So, we also knew what is the method how to get G of I at any particular temperature, or G or G bar. And then we finally saw that Kp depends on various parameters. It is affected by delta nu, how it is affected by P, and how it is affected by T. And in a very limited case, we came across Van't Hoff equation, which correlates Kp to the heat of reaction HR. And finally, we looked at phase equilibria, and we said that Gf is equal to Gg, which means that in the equilibrium state, every phase must have the same Gibbs function. So, with this we can now apply this knowledge to predict equilibrium conditions for various applications. In all these cases, we will require some data, and those tables are available. In some case, various books and websites will have that data. So, we will have to pull that data from there and solve the equation problems. So, that brings us to the conclusion of the fourth part of thermodynamics 2, where we have learnt about phase and chemical equilibrium. Thank you.